Wow!
This is very interesting, but I do not understand it. Perhaps I can start by finding out what torque is. According to the dictionary, torque is a twisting force that tends to cause rotation. This clarifies things a bit, but I still do not fully understand. Maybe there is a way to mathematically show what torque is.
So what is torque? Well, torque, a vector quantity, is a measure of the force that can cause an object to rotate about an axis. It is what causes an object to acquire angular acceleration. The direction of the torque vector depends on the direction of the force on the axis. Any of you who have ever opened a door has a basic understanding of torque. When a person opens the door, they typically push from the side of the door farthest from the hinges. Pushing on the side closest to the hinges requires considerably more force. Although the work done is the same in both cases, people generally prefer to apply less force, hence the usual location of the door handle.
Thanks for the explanation, but I would like to know how to calculate the magnitude of the torque vector.
The magnitude of the torque vector T can be calculated by taking the force and multiplying that by the radius and multiplying that by the sine of this angle.
Now that I know what torque is mathematically, let's look at some examples. How about we do problem 12.6? Let's do part A first.
So for problem 12.6, we're dealing with inertia. We have a normal problem of set axis for, we have a 25 kilogram solid door that is 220 centimeters tall and 92 centimeters wide. So for part A, it's asking us, what is the door's moment of inertia for the rotation on its hinges? So with our givens, we have the mass at 25 kilograms, the length at 220 times 10 to the negative 2 meters, and then the width, which is 93 times 10 to the negative 2 meters. But in our case, we're only dealing with the mass and the width, but because of the equation given to us for inertia, which is 1/3 times mass times width squared. So all we do for this, we just end up plugging in our givens, which is the 25 kilograms and 93 times 10 to the negative 2 squared meters. And so that would just give us your answer of 7.21 kilograms times meters squared.
Now let's do part B.
In this problem, part B, we're asked to find the moment of inertia of the door as it rotates around this given axis, which is 0.13 meters away from the hinges in the previous problem. So here are our given numbers from the previous problem, of course, as well as the second length, which is the distance from the edge to the axis of rotation. And by the parallel access theorem, we get this equation here. Moment of inertia equals 1/12 times the mass times the width of the door, not the length, squared, plus the mass again over the width over 2, minus the second length, which is once again this distance here, all squared. You plug in our numbers, the mass there, width, same thing, so on, making sure that you've translated all of your numbers from centimeters to SI units, as in meters, and check your kilograms as well. Keep going down, and you end up getting 4.61 kilograms times meter squared.
Interesting, but how about we try another example?
We have a torque problem. So we start out with the bicycle crank arm, 20 centimeters. Sprocket, the diameter is 25 centimeters. Initial velocity for this problem is 65 RPMs. Final velocity for this problem is 92 RPMs, and the time difference is 12 seconds. All right, so we start out finding dW. We have conversion to radians a second. And so we take the final velocity times the radians a second minus the initial velocity times the radians per second, and that comes out to 2.827 radians per second. And then in order to find the acceleration, we take dW, which we just found right here, and divide it by the time, 12, and we get 0.2356 radians a second squared. Alright guys, now to find the next part, AT, the tangential velocity, torque, one of those. We take the acceleration times the crank arm, bicycle crank arm up here, and we get 0.2356 radians a second squared times 0.2 meters. That comes out to 0.0471 meters a second squared, which can also be rewritten for 2 decimal places as 4.7 times 10 to the negative 2 meters a second squared. Alright, moving on to the next part of the problem. We have theta as dW squared divided by 2 times the acceleration. So we have dW squared, and then we have 2 times the acceleration, 0.2356, That comes out to the angle of 98.65 radians. From there we can calculate the length, the radius times the theta, and we get 12 meters as the total length.
Awesome. Thanks for all the help. Now I can continue to watch Benedict Cumberbatch aka Doctor Strange do some physics on YouTube. Yeet.